that's fine. Well, once again, welcome everybody to our final lecture of the 2020 part of our season. They resume again in January. To start off with a few forthcoming events, and of course, we're all looking forward to next Monday, the Great Conjunction, with Jupiter and Saturn only just over 6 arc minutes apart, the closest since 1663. There is a problem, which I found, trying to find somewhere to observe it, quite hilly around where we live. And Jupiter, the two of them, they're only at about 14 degrees or so above the horizon at sunset, which is around 1550 thereabouts. And they drop to the horizon by 6 o'clock or shortly thereafter. So good luck to anyone who wants to see them, and fingers crossed for the weather, because the next one's not until 31 October 2040. Just a minor caution, word of warning here. The usual warnings about looking anywhere near the sun if you're looking for the two planets before sunset, especially if you're using any optical equipment. I think everyone is experienced enough to know that. Meteorites, the Ursid peak is predicted for peak activity later the same night on the 21st, and also the following night. And then we have the Quarantids to look forward to, early January, 3rd of January. The 1400 hours, I think is the maximum peak on the 3rd. So the evenings of 2 and 3 Jan and 3 and 4 Jan should be reasonable if we're lucky. For anyone else interested in the practicalities of meteorite observing, my Sky at Night mag arrived today, as well as Stardust, and they do a monthly DIY feature. On this one, this month just happens to be how to set up a meteorite observing system using a Raspberry Pi and a little camera module inside a security housing. It looks very doable, so if you get that magazine, have a look at that. And of course, Paul Evans' excellent monthly YouTube series, The Sky in Whatever Month for December, is on at the moment, where he covers these details above and more. And of course, Terry Mosley has his Sky Note series, which we just mentioned, Stardust magazine. That's for January to March 2021. ISS transits, the Heavens Above, another excellent site, lists a series from 18 December, a couple of days time, to 7 January. They're quite low up until about Christmas Eve, but then they get better after that, so plenty there to look out for. Now we come to our main speaker, who is Dr. Gavin Ramsay from Armagh Observatory and Planetarium, with the title of his talk being Gravitational-wave Optical Transient Observer. Hope I got that correct. A few details about Gavin. He did his PhD at UCL, Mullard Space Science Laboratory, using data from the ROSAT X-ray satellite to study magnetic accreting binaries. After several years at the University of Utrecht, he returned to MSSL and came to Armagh in 2007. He still studies accreting binaries, but has led several wide-field photometric surveys and also uses Kepler and TESS data to study the activity levels of solar type and low-mass stars. He leads Armagh's contribution to the GOTO project, that's GOTO capital letters. And lastly, as before, if you have questions, please post them using the chat button, and then we can refer to them after the talk. Okay, Dr. Ramsay, that's it. So over to you.
Thanks. Okay, so I'm going to talk about a project called the Gravitational-wave Optical Transient Observer, which is a bit of a mouthful. So it's shortened to GOTO. It wasn't my acronym. So GOTO is an international project. As you can see on the right-hand side here, there are many UK institutes, as well as the National Observatory of Thailand, Turku in Finland, and Monash in Australia. So I'm going to be talking about what we're doing, which is looking for the optical counterpart of gravitational wave events. But I'll explain, this will become clear what this photo shows. So I'm going to start off by, now how do I, okay, so I'm not quite sure how to keep on going in this. I've had this problem before. Let me stop sharing. Now I'm going to try and go back. Oh, okay. So, and now I don't know if I'm actually still sharing this.
You're actually not sharing at this moment, Gavin.
Okay, right. So I know that people get this every now and again, and I'm not quite sure why it is. Okay, so there we are now. So hopefully you can all see this. I'm going to start off by just going through what gravitational waves are and how some fantastically intelligent people go about doing this. So gravitational waves are generated by massive objects kind of basically orbiting around each other. So many of you, I'm sure, will have seen this diagram or something like it, where you've got massive objects and they're basically distorting in space-time. And if you've got more massive objects and they're very close to each other, say two black holes orbiting around each other very quickly, gravitational waves are going to be emitted. So they were predicted more than 100 years ago by Einstein in his theory of general relativity. And so we've known actually for many, many years that gravitational waves exist. So, for instance, in Mercury here, this is the orbit of Mercury here, it was found prior to general relativity that Newtonian dynamics couldn't actually explain the orbit of Mercury. But general relativity with gravitational radiation, it does fit it precisely. Now, about in the 70s, the Hulse-Taylor binary pulsar was detected. So in this system, you've got two neutron stars, which are also pulsars, so they're rotating very rapidly. And by measuring the pulsations over time, they've been able to show that this binary pulsar system, which is an orbital period of 8 hours, is shrinking over time at exactly the same rate as Einstein predicted. So how do we detect gravitational waves? So basically, it is incredibly difficult. You're trying to measure the separation of 2 points with tiny fractions of the size of the proton. So it's exceedingly difficult. And it's why it's taken so many years for people to actually do this. So on the left-hand side here, this shows a photo of Joe Weber and some colleagues with one of his cylinders of aluminium. And so the idea was to have these cylinders and vibrate them at a specific frequency. And as gravitational waves swept past the Earth and its detector, the frequency would change by a tiny but measurable amount. Now, we now know that these systems were never, ever going to detect gravitational waves. His group actually thought and announced they detected the supernova 1987A, but that was shown to be completely incorrect. So how do we detect gravitational waves? So this is I'm going to show you a nice video done by Caltech, and it's basically describing the Michelson-Morley experiment, which some of you may have done in school or in university. And this is actually a nice demonstration of the concept of how we go about doing it.
To measure this stretching and squeezing, Ray turned to a device called an interferometer. A laser beam is split and sent down a pair of long perpendicular tubes, each precisely the same length. The two beams bounce off mirrors and recombine back at the base. The light waves come back lined up in such a way that they cancel each other out.
When you add them together, you get nothing. You get a zero, a big fat zero. No light gets detected at the photodetector.
But when a gravity wave comes along, it distorts space and changes the distance between the mirrors. One arm becomes a little longer, the other a little shorter. An instant later, they switch. This back and forth stretching and squeezing happens over and over until the wave has passed. As the distances change, so does the alignment between the peaks and valleys of the two returning light waves, and the light waves no longer cancel each other out when added together in the recombined beam. Now some light does reach the detector, with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
Okay, so hopefully that's a nice explanation of how we go about doing this. Oh, right. So now I'm going to go on to LIGO, which is the Laser Interferometry Gravitational Wave Observatory. So this is the observatory which I'm sure you'll have heard about the results. So there's two sites, as we'll find out, one in Washington State in America and one in Louisiana. And the next slide gives you, again, courtesy of Caltech, this explains much better than I could do of how it works and what they found.
Gravitational waves were predicted by Einstein almost 100 years ago. A gravitational wave is a ripple in the fabric of space and time. It's produced somewhere in the distant universe and travels across the universe. When any massive object moves, it's changing the nature of space-time. That's what Einstein told us.
So you have a motion that stretches space in one direction and compresses space in the other direction.
Nobody really believed at the time of the prediction that you could ever detect them because the size of the effect is so small. It was what we call a chirp, and it was strong.
Everybody thought it was a fluke. It was too good.
And I thought, my God, this looks like it's it. Oh my gosh, this is real. It took us 25 years and 2 detectors to finally detect the gravitational wave. We have interferometers, one in Hanford, Washington, one in Livingston, Louisiana, to detect the stretching and compressing of space.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off. However, what's even more remarkable about this is what we detected.
We have observed gravitational waves from 2 black holes forming a larger black hole.
For the first time, 2 black holes spiraling together, coalescing, merging, creating wild oscillations, a storm in the fabric of space and time.
They're moving at the velocity of light, damn near that velocity. 30 solar masses moving that fast. I mean, they're putting out incredible amounts of energy.
And when they collide with one another, they produce a bigger black hole, but they also produce gravitational waves. And in that process, about 3 solar masses just disappears and goes into gravitational waves.
Oh, it's going to be amazing. We have always said that this is going to be a field called gravitational wave astronomy.
Gravitational waves carry information that you can't get from any other way. A supernova, 2 neutron stars colliding, even the Big Bang itself, the beginning of the universe, all produce gravitational waves.
This first detection by LIGO is the very first step. It's just the start of the story nature is about to tell us.
I would love to see Einstein's face. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field of gravity, is in his equations. Just imagine that. To me, that's a miracle. It settles the question for astrophysicists. Do black hole pairs form? Yep, we got one.
So it generally takes many years for people to be awarded the Nobel Prize for these things, but the LIGO and the gravitational wave people, they won the Nobel Prize for physics a matter of years after this kind of announcement, because it was such a spectacular achievement. So one of the problems with these gravitational wave detectors is they can't really predict or locate where in the sky the event took place. Okay, so this is a map on the left-hand side here. Yeah, I'm just found my cursor here. This is obviously the Milky Way here, and this is what we call a confidence contour region of where they thought the black hole merger was. So as you can see, it's hundreds or thousands of square degrees of sky. And on the right-hand side, this just shows you a more kind of accurate way of describing it. So the problem, and if we could actually find out where in the sky the event took place, and actually identify the galaxy for where it lived, and then you can get the redshift, etc., you can actually find much more about the merger event itself. However, black hole mergers are not predicted to show an immediate optical counterpart, which makes the whole process extremely difficult. However, if the gravitational wave event was due to a neutron star merger, then it's predicted that there would be an optical counterpart for this event. So I'm sure many of you will remember when this was announced in 2017, the merger of two neutron star events. This made the front pages of all the websites, all the newspapers, because it was quite a stunning achievement. And in this case here, they did predict an optical counterpart, and this shows you on a sphere where they thought the burst took place. So the initial LIGO observations still covered hundreds of square degrees. So with Virgo, which is a European detector based in Italy, they were able to narrow the confidence region down. And these are X-ray limits, which I'm going to come on to shortly. So this plot here, this image is a Hubble Space Telescope image of the galaxy for where it was found several months before the event. Then I think it was about 12 hours later that the Schwab telescope in Chile was trying to follow up, find the optical counterpart, and they found this new transient here, which turned out to be the optical counterpart. So this was a stunning achievement, and when it was found, basically every telescope, every satellite which could observe this, they were studying this source. So I'm going to mention, it's a bit of a buzzword called transients. I'm going to just say what they are. So transients are star-like objects which suddenly become visible. So it's quite simple. But the problem is there are many, many different types of transients. So I'm going to come on to the end and talk about cataclysmic variables, something which I've been looking at for many decades, and supernova are another kind of transient. So what did astronomers find out from this event, which was actually one of the best studied astronomical events ever? So what we're seeing here in this this is going to be a movie showing you how the spectrum of this event changed over 20 days or so. So we've got blue light here, and we're into the infrared here. And this is just a spectrum of this event. So it's like a rainbow of this event. Okay, so here we go. So it's a very rapid decline in the blue optical flux. And then what you'll find is, as you can see here, you can start to see various lines, absorption lines, starting to appear. And from these absorption lines, you can actually determine what this stuff is made out of. So it's still bright in the in infrared there, but it's now becoming very faint. So this is 7 days, okay? So on the right-hand side, this shows you the periodic table. And this just shows you how the different elements are thought to form. So hydrogen up here, this is made in the Big Bang, and then there's helium, which is also made in the Big Bang, but also dying stars. And what this event showed you was that many elements, including gold, many of you may have a ring made of gold on your finger. Well, this was possibly made in these merging neutron stars as well. And then when you get to the very heavy elements, and also radium, but also uranium, they were made in merging neutron star events. So what is the bigger picture? So it was alluded to in one of the movies that we've now moved into what's called multi-messenger astronomy. So most of the astronomy which mankind has done forever essentially is through electromagnetic radiation. So it's optical, X-rays, radio, infrared. But now we have a different way of looking at the universe. This is gravitational waves. And also neutrino events are starting to become observed as well. So this is all kind of opening up a new window in the universe. So what this plot here shows you, this is the neutron star merger. This is time along here. This is only from here to here. This is 16 seconds, okay? So this is really not very long at all. And what this shows is this is the frequency of the merging event rapidly becoming kind of faster and faster until it merges here. But what we show on these three plots here, these are our X-ray satellites and gamma ray satellites orbiting the Earth, and they detected this event too. But it wasn't at the same time as the merger event. It actually took place just less than 2 seconds after the merger. So this is giving insight into the actual merging process, more detail about what actually happened, but it's also allowing us to test theories of how gravitational waves propagate through the universe. So when you're dealing with such rapidly changing and rapidly time variable kind of astronomy, you need to be quick and you need to be automated. You know, there's no point in waiting to get phoned up and getting your telescope started. No, it needs to be automated. So this up here, this shows you Hanford, the signal here, Livingston and Virgo. These are future ones. Basically, they're gravitational wave events. Their stream is being analyzed in real time. So what they do as the stream is being made, it's being compared with a bank of template events. So they've got a whole different possible combinations of event which predict the signal, the change in the frequency, and they're trying to find the proverbial needle in the haystack. So if there is an actual event, this then rapidly goes through a verification quality flagging situation, and this gets fired out to observatories both on the ground and orbiting the Earth. Now this just shows you a schematic here. So this is 1 minute after the merging event. Okay, so 1 minute. Okay, a preliminary alert is sent out within roughly 2 kind of minutes of it happening. Then various processes then start happening. Now they try and estimate, well, what are the masses of the components which have merged? There's human vetting, which goes on. And then there's another alert sent, or sometimes the initial alert is retracted because actually on human vetting says, well, this is actually not a real event. And then further updates are done during the next week. So if you want to find the optical counterpart, you need to be fully automated, fully robotic, and you need to have an automated scheduling of where you're going to point. You also need to have a telescope with a wide field of view, and it's going to help if you've got machine learning to help identify what you think are transient events. So one of the key things is how to distinguish between the events which you want to detect, which is an event associated with the gravitational wave emerger, and separate from supernova, which are hundreds at any, or thousands at any one time known. And there's flare stars, there's active galactic nuclei, etc., etc. So it's an extremely difficult task to perform. So one of the key ways to do this is called difference imaging. So it's quite a simple technique. This shows you an example from a couple of years ago. This was known as 2018 COW, COW for short. This was discovered, I think, by Stephen Smart's group in Queens. So this was the discovery image, and this is it here. And what they do is they've got a bank of reference images of the same part of the sky. This is their reference here. And then what you do is you basically subtract the reference image from the discovery image. And then if this process is done well, you're left with, so these stars, they all get removed, and you found a transient here. So this can take into account different atmospheric conditions, so as differences in seeing. It's relatively quick from a computational point of view, but you do need good reference images. So I'm just going to go back to talk about transients and how difficult it is to sort the wheat from the chaff. This goes back 12 years. This was a pilot study with the Canada, France, Hawaii telescope, and they were doing a mini kind of survey searching for transients. And so 3/4 of their sources which appeared as transients were asteroids which weren't known. Okay, so if an asteroid's moving around, it won't be in your reference image, so it's flagged up as a transient. So fortunately, we now have various tools which allow us to determine if a transient is actually hiding as an asteroid. But in their study, they also found 20% of their transients were known asteroids, 4% were variable stars, and only 1% were actually real transients. Most of these were supernova, and a fifth were active galactic nuclei going into outbursts. So it might sound a very simple thing to do, but it's exceedingly difficult. So I mentioned variable stars briefly, and I don't want you to look at this in detail, but I'm just going to show you that. So I've done a lot of work in variable stars, and so there's some variables which are eruptive. So these are flare stars here, young pre-main sequence stars, and then you get the cataclysmic variables, which are also transients as well. So they're the dwarf novae, they are recurring transients. Okay, so I'm now going to go on to talk about the Gravitational-wave Optical Transient Observer. So this was initiated by the University of Warwick in England and the University of Monash in Melbourne, Australia. And they had this plan 6 years ago to actually build a facility which would actually find the optical counterparts of gravitational wave events. So in the next year after that, Sheffield, Leicester and Armagh were able to join this team. Now Armagh was able to join it through investments made by the Northern Ireland Executive through what was DECAL and is now the Department for Communities. And since then, it's been joined by the National Observatory of Thailand, Turku in Finland, as a group in Manchester, Portsmouth, the IC in the Canaries. So it's an international project. So the prototype, as I'm going to discuss, is built on La Palma, and it's next to Super Wasp, which was started by Don Polacco, who was in Queens and is now in Warwick. So the telescope here, this is the William Herschel telescope. In the 80s, this was one of the premier telescopes in the world. This is the Gran Canaria telescope, the GTC. This is a 9-meter telescope. This is, if you ever have a chance to go to La Palma, do go and check out this telescope here. It is quite awesome. And you could literally eat your dinner on the floor. It is so impressive. And then this is the Nordic Optical Telescope. This is Swedish telescope. And then, so the Warwick facilities, they're all here. So what is, so the prototype, the prototype was, the first light was, I think it was about 2017. And so what we've got, the prototype was 4.4 meter telescopes all on the same mount. So this means you could slew all the telescopes very fast, and it's got a clamshell dome built by Astrohaven, which we'll come back to close to the end. And they're a company which specializes in making these clam domes. So the idea was that this would be a very cost-effective and scalable way of rolling out increasing numbers of telescopes. So the idea is to cover the sky as rapidly as possible. If you're going to observe these kind of events, you need to get quite faint. So in the dark moon, we get down to 20.5, sometimes 21. So as I've said, everything needs to be fully robotic. Gravitational events need to be detected automatically by our software, and the data is downloaded to Warwick in real time. So as many of you will recognize this image of Andromeda, this is only part of an image of one of these detectors on one of these telescopes. So I'm just going to briefly mention now about observing strategies, which is actually sounds very dull, but it's actually key to actually ensuring you have a best chance of observing the object, the transient which you want to do. So this just shows you the neutron star merger. So the whole sky is divided. We've divided it up into tiles. So the key is every time you go back to the same part of the sky, you fall onto the same tile. Okay, so it means that when you're subtracting reference images, it's much easier if it's falling onto the same tile. And this shows in this particular event that we could observe most of the confidence region in less than 10 images, which is very good. So what we also do is observe gamma ray burst events. And what this shows you, this is the kind of questions which our software is thinking, and how do we go about deciding how we're going to observe. Okay, so if it's a gravitational wave event, it goes through the pipeline. Does it know anything more in detail about the objects? Yes or no? Has it got a neutron star? Yes or no? Has it got a distance less than 400 megaparsecs? So these are the kind of questions which the software is asking, and depending which box you end up, the actual observing strategy will be subtly different, which is crucially important. So I'd mentioned artificial intelligence earlier on. So this is going to play an increasingly important role when more and more data starts pouring in. Some of you will have heard of LSST, which is a huge 9-meter telescope, which will be providing a deluge of transients. So artificial intelligence is key to the success of all of these projects. But all projects which are doing this currently, there's an element of manual verification. So this just shows you a cutout of our manual verification system. So this shows you an event which took place on the 3rd. So what this shows you, this is the discovery image in this case. This is the reference image. And this is the subtracted image. So we found a transient here. So for comparison, this is the Pan-STARRS image here. Nothing there, but this was in fact actually a previously known transit, almost certainly a supernova, and there's probably a faint galaxy here. So we can do this more or less 24/7 because we've got a team in Australia, there's people in Thailand, and then there's people in the UK. So this allows people to do this almost at any time of the day. So I mentioned La Palma, and La Palmas are normally a very safe environment. It's generally lovely, but sometimes it can be actually extremely dangerous. This was when we had a couple of our students there, 2 or 3 years ago, and they were help doing verification work. And there was an ice storm which lasted snow and ice for a week. And this is quite a classic image of one of the jeeps up at the top of which was basically left. Uh, and then in July this year, there was a fire on La Palma, which did make British news as well. And so this shows you the Grantican telescope, one of the biggest telescopes in the world. This shows you quite an alarming position, but actually the fire is some way down the mountain, but the whole site was evacuated for several days. And of course, back in March and April, the whole site was evacuated for COVID reasons, and no observations were being made. So phase 2 of GOTO, so this is GOTO now. So this image was taken basically a few kind of weeks ago. So now we have 8 telescopes on the same mount, covering 40 square degrees. We've actually got better, newer telescopes than the original 4. They're much better quality. And so in January this year, the GOTO consortium got awarded £3 million from the one of the UK research councils, SDFC, and this was to build a second node in this dome here, and then 1 and possibly hopefully 2 nodes in Australia. So this shows you the location here, La Palma here, Siding Spring here, and this will allow us to cover both kind of hemispheres. So phase 3, when we get this built, this should be happening by the springtime. We're very hopeful that this will happen. This will give us 80 square degrees of the sky simultaneously, and then planning permission has just gone into the council on Siding Spring for our first node in Australia, and we hope to get going there by northern summertime next year. So this will give us fast cadence across the whole visible sky. So this, again, these are images basically from just a few weeks ago, and this shows you the next dome being shipped from California to Australia. I had to get fumigated, all that before it got sent on its way. And this shows you, this panorama image here shows you the Siding Spring site. It's pretty boulder ridden, and there are quite a lot of snakes, etc. there. This is the Uppsala dome here, which is going to be removed, I think. This is a telescope from the Japanese Space Agency here, and we're going to be going into this site here. So how does GOTO compare with other projects? So this is the full moon, half a degree in diameter, giving you 0.2 square degrees. So GOTO in comparison, just 2 nodes on the Palma, this is 80 square degrees. So I've mentioned LSST. This has a huge mirror, but it has a 10-degree field, and it won't have the cadence which we have. ZTF, some of you will have heard of this. This is in California. It's discovering many transits, got a simultaneous coverage of just less than 50 square degrees. Now, Black Gem in Chile, this is doing similar work, but this has 3 telescopes, and they're going deeper than us, but their field of view is much smaller. So there's no other project which has the combination of all sky coverage, north and south, rapidly. Every few days we'll be covering the entire sky, and with sufficient depth to actually detect these faint transient events. So, of course, I've been talking about some specific events which the whole project is aimed at, but there's other science areas which people in the consortium are going to be looking at. One of these is fast transients. So this plot here shows you how rapidly they're called kilonova, how rapidly they drop in brightness compared to all these supernova here, which are much more leisurely in declining from their brightness. So there's many other luminous supernova which we're interested in. Tidal disruption events. This is an artist's impression here of when an object, a star of some kind, gets basically swallowed up by a central black hole of a galaxy. So active galactic nuclei can be showing interesting effects. There are gamma ray bursts, and there's neutrino events. This is Ice Cube here. And so this is already detected neutrinos from active galactic nuclei. There's pulsar binaries detected by the Fermi satellite, and many of these things will need rapid spectroscopic coverage at an early stage, which maybe there's going to be potentially a new telescope on La Palma based on the Liverpool telescope, which is going to be dedicated to getting spectroscopy of rapid varying transients. So I mentioned cataclysmic variables. So some of you may have heard me talking about these before. This is some work which my student Chris Duffy's been looking at using GOTO data and others, including amateur data here. This is there's quite a lot of AABSO data here. So this shows you the light curves over several years of 3 ultra compact binaries. This is an artist's impression here. We've got a white dwarf and a white dwarf. There's accretion going on here. And these 3 particular systems have orbital periods which are very, very close to each other. KL drag goes into outbursts every 60 days. It's pretty clockwork. Then this one here, it's not quite as regular as 60 days, but this one here, this is actually very different. It shows very rapid decreases in flux here and again here, and then it's quite stable for an entire year. Now, by looking at these long-term light curves of these events, we gain insight as to what is actually causing the instabilities in the accretion disk causing these outbursts. So this is my second last slide, and I'm going to go back to LIGO and black holes and neutron stars and measuring their masses. So before LIGO, we knew that there was many neutron stars in our galaxy which had masses between 1 and 2 times the mass of the sun. And then LIGO is now discovering more of these neutron stars. And in our galaxy, we've known for many years that there are some black holes. They're in binary systems, and they have black hole masses of 5, 10 or so times the mass of the sun. So before LIGO, we didn't really know that these black holes existed. And now we know that we've got black holes of 20 masses, so 30 masses merging to give higher mass black holes, and this is giving profound information to how black holes in general are formed. So my final slide is looking ahead to the future. So LIGO and Virgo stopped their last run called 03 in the jargon. So it was stopped prematurely in March because of the lockdown. Both of these detectors are now being upgraded, and I think there are delays because of COVID, etc. But they are aiming to get back online much more sensitive by the summer or the autumn of 2022. Now, the exciting thing which is going to be coming along and maybe 2025, 2026, is there's going to be a duplicate copy of LIGO being put in India, and Kagura, which is the Japanese detector, this has come online, I think, now, and it's going to start making an impression as well. So we need to be fully deployed by the summer of 2022 at the very latest, but we are very confident that we'll get there before that, so we're going to be up and running before then. And I'm going to stop, and I'm going to take any questions, and I'm going to stop sharing.
Unmute, Danny.
Yeah, that's great. Thank you. Thanks very much, Dr. Ramsay. That was a very detailed, interesting overview of your subject. We have an initial question from Terry. You'd like to go ahead, Terry?
Okay, I just sent it in the chat. I'm just wondering, whenever GOTO detects an optical counterpart, is it automatically going to alert other wavelength observatories like X-ray, gamma ray, microwave, and so on?
And so what happens when these events happen, it becomes a bit of a feeding frenzy. And then, so there's various routes to actually tell the rest of the world what people have found. And then you'll find basically many projects announce if they've discovered anything or not, what the location is, what its brightness is, or if they've not found anything at all. And this is very important when they're coming to actually get spectra of it, and so other groups and satellites can decide what they want to do.
Right, great, thanks.
Tom Gao, there's a message, or Tom. I think you'd need to unmute if you want to expand on it. Is Tom there?
And so I could read this out if Tom can get on. So Tom says, why do astrophotographers say air glow is from gravitational waves? I must admit, I haven't heard of astrophotographers saying air glow is caused by gravitational waves.
No, me neither, I must say.
Me neither either.
I hear it quite a lot when I see descriptions that they'll take pictures of air glow and they'll say that this is one of the an effect of gravitational waves, which I always thought was strange. I never understood that.
No, I'm afraid I've not. I haven't heard of that one. Sorry.
Okay, no problem. Thanks.
I thought air glow was fairly well established as excitation of molecules high up in the atmosphere, just glowing constantly all the time by a combination of radiation from other sources in the universe, or maybe even other effects. I don't know, but I thought it was maybe some of the photographers know more about that. But there is a constant background air glow, which is why you can never get a totally black sky here on Earth. I thought it was fairly well known. Paul, Danny, do you know?
Less than what you mentioned, Terry, I must admit.
Yeah. Paul's muted.
Yeah.
Terry?
Yeah, Michael?
Go ahead.
I think Tom might be confusing gravitational waves with gravity waves.
Oh, in the Earth's atmosphere.
Yeah, I did a very. I thought that I did a very brief search on Google, and it does mention gravity waves and air glow.
Yeah.
So it could be it's gravity waves.
So waves in the atmosphere itself, not.
Yeah. I think they're pressure waves.
Not stretching of space time.
That would make sense. Yeah.
David Moore is saying much the same. Do you want to expand on that, David? David?
I think you can hear me now, yeah?
Yes, go ahead. Go ahead.
Yes.
Yeah, it's what people were saying there, that you get these ripple effects, very dark sky sites in the air glow itself. And it's gravity, they call them gravity waves. There's nothing to do with gravitational waves. It's probably just density fluctuations in the air at high altitude. Pity they use the same term.
Yes, it is very confusing.
Gavin, could I come in with another one since we're on sort of all on speaker? You showed a graph there of one of your cataclysmic variables with a long stable period. I'm just wondering, was that a ZCAM variable or was it something like a ZCAM variable?
That's a very good kind of question. That seems to be an analog, and so they're all kind of, the ones I showed, they're all kind of hydrogen deficient. They don't have any hydrogen. So, but they seem to be showing ZCAM effects as well, despite being kind of hydrogen deficient. So you're right. Yep.
Okay. Yeah.
Paul, did you get a chance to ask yours there? I missed it.
No, sorry. I for some reason I initially sent it to everyone in the waiting room, which wasn't very helpful. But one of the little quirks of things. No, it was just a thought, actually, Gavin. You mentioned that you expected to detect many more supernovas than what you're actually looking for. And it kind of reminded me of Charles Messier, who, of course, was only interested in comets, but catalogued a great many sort of nebulae and galaxies and whatever, and that's what he's more famous for. But so, having collected that data, would you do anything with that, like pass it on to people who are interested in supernovas and stuff?
So there is kind of an IAU dedicated site run by the Weizmann Institute in Tel Aviv, which basically collects new information about new supernova, and then people can do whatever they like with that. So we are contributing to that. We announced one this morning. Yes, so we're definitely doing all that. Yeah.
Oh, fabulous! Thank you,
Andy. Believe you've one there listed.
Sorry, just trying to find me on mute there. Yes, Gavin, is there any indication that gravitational waves are influenced at all by dark matter? I mean, have they helped our understanding of the dark matter, or just further confused the whole thing?
And the short answer is I don't know. But I do know that by comparing, say there was the 2-second delay between the X-ray detection and the merger, the gravitational merger, this is helping understand how gravitational waves propagate through the universe. And so my guess is that this will have some influence on how we understand dark matter. But I'm not kind of an expert, so that isn't a definitive answer.
Okay, thanks, Gavin.
Gavin, I just wanted to ask a question. With the Ligo out of operation effectively until 2022, does that mean you have very little to do, or have you?
Oh no. I mean, so we're now it's full steam ahead of making the new kind of sites. The second site on the Palma, the first site in Australia. It sounds easy, but it's actually full of bureaucratic hurdles, as well as technical kind of issues. I mean, just getting even site agreements, just getting people communicating with the people who are making our domes. I mean, it can be a nightmare. We've got 2 project managers who are devoting some of their time to this in Warwick, and they are fantastic because they have the patience of saints. But to answer from a more scientific point of view, is that what we'll be doing over the next couple of years is actually doing mini surveys, and so relatively small parts of the sky, well, still thousands of square degrees, and then really starting to hammer them with high cadence, and we think we'll get some very interesting new kind of objects, especially when we start looking at the sky in different colors as well. So we're going to be opening up a new route for us, which will do lots of exciting things, but it's also a learning process, because you want to be, when you get to the summer of 2022, you need to be everything running like clockwork. And that, it sounds simple, but all these things, there's pitfalls, things go wrong, things break, something that doesn't work, blah, 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 blah. There's pandemics. So there's lots of things which we need to do to ensure this happens in a 1.5 time. But we'll be getting signs as we go along.
And if you don't mind me asking another question, Gavin, you mentioned earlier about maybe, how artificial intelligence could impact the way you operate the system, or the system will operate. Is that something you're going to be working on as well?
Oh yeah, we've got some very good PhD students who are working in Warwick and also Sheffield and in Monash, who are very, very smart, who are able to bring new influences and techniques to try. And so you're basically trying to sort out literally the weed from the chaff from the wheat, or vice versa. Yeah, because I mean, in the case of LSST will be having tens of thousands of of new transients every night, but that's because they go so deep. And that's just going to be an absolute nightmare to try and obtain anything interesting, because most of the events won't be able to be followed up.
Okay, yeah. Thanks, Gavin. That's interesting.
Could I ask another one, just wondering what the resolution of GOTO is? I mean, if you're imaging, getting things in the Milky Way, will you be able to distinguish between, you know, some of the star fields which are very, very dense?
Yes. So the pixel scale's 1.2 pixels per arc second. So it's pretty good.
Right.
And then I noticed that someone's asking about Starlink.
Yes.
Okay, so this will be becoming a problem. We put out on Twitter some observations of Starlink trails, and yeah, it's becoming an issue. And I think they did have some ways they were going to paint their satellites black or something, but it was only reducing the brightness by, whatever it was. And so it's becoming a serious issue. Yeah.
Any further questions? Anyone? Just something that occurred to me, Gavin. It's slightly off topic, I suppose, but looking at the picture you posted of Siding Spring and the spot for the anticipated new observatory.
Yes.
I know it's a sensitive subject, but often because of the remote areas that the scopes are put in, there can be conflict or disputes with first populations of various regions.
Well, that's a very good question. So in the case of La Palma, the Spanish colonizers, they wiped out the natives. So that's not something which we had to consider within La Palma. In the case of Siding Spring, so Siding Spring goes back to the 60s when the Australians and the British were building telescopes there. And in those days, it didn't really occur to anyone to actually involve the original descendants from original inhabitants. I believe one new project has started to do that in Siding Spring, and we hope to be consulting or informing them what we're doing in the next few months as this goes through planning permission. So you're right to bring this up. In the case of Hawaii, and also I think in Arizona, this has become a real kind of contentious issue. It's a very good question. So there's a question here, direct message from Michael McCreary. How are we interpreting gravitational waves compared to the optical waves? Well, this is basically goes back to looking at when you get the merger event and then comparing it with, say, the X-ray detection, and you can do this to within a tiny fraction of a second. So this is telling us something important about how the merger, the physics of the merger, and also how the gravitational waves propagate through the universe. And neutrinos will be coming along and allowing us to do accurate comparisons with gravitational waves and also the electromagnetic spectrum as well.
Well, one more just occurred to me. Going back to one of your pie charts, you listed hostless transients. I'm wondering what they are.
Well, they're basically when you find your transient, you can't find any evidence of a galaxy in the background.
Right. So it could be what an atmospheric effect or a satellite flash or a head-on.
No, it generally means that the background galaxy is just too faint. But if you went much fainter, maybe if you had a Hubble Space Telescope image going deep, you would actually find there is a galaxy, but it's just very, very faint because it's got a high redshift or it's just a faint galaxy.
So if they're coming then from galaxies that are so incredibly far away, they must be very powerful. Is it not something that's worth chasing up then to try and get a very, very deep image and identify the galaxy?
So when events like that take place, so gamma ray bursts, for instance, so gamma ray bursts are now being observed to very distant redshifts, and it takes so they would quite often be hostless transients, but then when you start getting the world's biggest telescopes and getting deep images, then you start to detect, oh, there is the host galaxy.
Right. Okay.
And then in the case of the gamma ray burst, you can then say, well, this is a gamma ray burst from a galaxy with a redshift of 7 or whatever it is. And that's very important in understanding about that gamma ray burst and stuff.
Great, thanks.
I just wondered, just following on from what Terry was saying and you, Gavin, is it possible then some of your measurements might help, tie down distances to galaxies and things? And, how far is your instrumentation going to reach out into the universe?
So generally, if you can get a spectrum of your galaxy, that will normally give you the redshift.
Okay. So, your detection events are not going to refine that any, not going to refine those distances any?
So we're the first part, we're part of the discovery phase. And then to make further investigations and more detail, you need to get a spectrum of the host galaxy or the source itself. So it's by imaging and detecting the transient, that's what we do. And then to get the most information, you need to get a spectrum.
So, for example, tying up your data with what LIGO would say, for example, doesn't refine those distance measurements?
No, but it means that we need to be, as a previous question I alluded to, we need to be announcing to the world, or actually having time on telescopes which can give us the spectral information from other telescopes. So it's all part of a wide endeavor to actually do this. And there's no one single group who can do this alone. It's a multi-telescope and multi-continental endeavor.
Okay, I understand.
And then I've got another question from Michael McCready, director. Is there any instrument on the James Webb telescope to look for gravitational waves? I suspect, what my understanding is, the field of view of the James Webb is not big, but what it will be able to do is determine and get the spectra of distant faint red objects. And hopefully the James Webb Space Telescope, it will be launched in I forget when the latest launch date is, but hopefully it's going to be launched in the near future. But people have been saying that for a long time.
Mm-hmm. Certainly have. Unless you can see any more questions, Gavin, I don't see any. So could I just say thank you once again? And I'm sure we'll all be looking forward keenly to your results and the results of all the other scopes once they come on.
We do send some stuff on our Mars Energy Planetarium's Twitter and Facebook. So keep on looking for new results if anyone's on these social media sites.
We will do. Thank you again.
My pleasure.
Just remains for me to give you quick details of our forthcoming talk on the 6th of January. Our own Professor Stephen Smart, and the title of his talk is Searching for Kilonovae in the Nearby Universe.
I think you might be getting a similar talk to mine then, but from a different perspective.
Oh, it's good to hear all the angles. So in the meantime, good luck for next Monday, the 21st, everybody. Being interested to see various images coming in from that. And best wishes to all for Happy Christmas. and if anyone wants to continue talking, we can do so. We're not time limited. All right. Thank you.
Okay, thank you.
Thanks again, Gavin. Bye-bye.
Thank you, Gavin. Thank you very much.
My pleasure. My pleasure.
Yeah, thank you, Gavin. Very interesting. Good
Cheers,
luck
thank
with
you.
your work.
Thanks.
Hi guys, just one small thing on that planetary conjunction. The weather prospects aren't bad for Sunday, and now you only get 9 arc minutes, not the full 6. That looks like quite a reasonable proposition weather-wise at the minute for us.
Yeah, good practice.
Monday looks dreadful, by the way.
Oh, right.
Well, that's scary then.
Yeah.
For somebody in Belfast, where are you recommending we should go?
Well, I was going to try up at the the Divas Cafe.
Oh, yeah, right, okay.
But
as long as it's as windy as it was the last time, Danny.
Yeah. If I get a chance, I'll go up tomorrow or Saturday and just check the angles.
Is the cafe open at that time? Or are you going the car park, the entrance?
Don't know. I'll let you know if it is open or not. But
I wonder if you might be able to use the car park at the entrance.
You could, yeah, on the other side of the road.
On the other side of the road, maybe.
It's always open because there's no fence.
You reckon that'll give you a clear view then over Loch Ness or whatever?
I'm not sure. I need to check out the angle. I'll bring my compass and I'll let you know once I've been there.
That'll be good, Danny. Yeah, because I might be interested in going up there myself.
For anybody that's interested in seeing it from the proper part of the world, the Tesco car park in Bangor is absolutely spot on. It gives you. I was there last night. We practiced with the telescope and all down, and it was as clear as day last night.
Where'd you go, Andy? Tesco's
car park in Spring Hill. Perfect view. It's elevated, so you're sort of looking down over the southwestern horizon. It's pretty good. Just as you come into Bangor, Tesco's is on the left-hand side.
Yeah.
You'll see the Tesco sign, and there's a big car park. I just set up at the barrier last night, set the telescope up, and had a go.
Have you not got a lot of light pollution there? No.
Sure, you're not worried. You're only taking a picture of the planets. To be honest with you, it's not a factor. But the quality of the images are hopeless. Like, I mean, it's so low down. It's about 15 degrees up. It's really poor, but you do get a good view. And if it's going to be as clear as it was last night, it's perfect. But hey,
would there not be a lot of traffic there, Andy?
There's nobody. I mean, I had a whole row of cars, and my car was the only one parked on it. Now there's nobody in Tesco's at that time. It's what time is it? 4:30.
There's obviously no Primark there then, Andy.
There's bog all in Bangor. I mean, everywhere's closed, and it's not that there's anywhere that you would go to anyway. But it's hopeless. It really is. Bangor's on the doldrums, I'm afraid.
Surely on the Monday just before Christmas, Andy, it'll be pretty busy.
No, not Terry.
Seriously?
You'll be fine. Yeah, you'll be fine.
All the people
I was there last night. I'll be honest with you, Tesco's was busy, but not that part of the car park. But I don't want too many people coming down anyway, because you're only going to get in the way. So
I was wondering, Andy, if you're up in Scrabo or somewhere like that, would you have a view?
And no, Bernie asked me about that. You have to lumber your gear up. If you're going to go up and try and take a picture, do you really want to take a telescope up Scrabo? I've done it before, and I'm going to Tesco's car park, I'll tell you that. But, it's a beautiful southwestern horizon. Yes, there's lights, and yes, there's cars and all the rest of it. But the image quality isn't going to be good. It's just so low down in the atmosphere. It's going to be crap, to be honest with you. But unless you want to go up a mountain.
What about Craigavon or somewhere like that? No?
Yeah, there's good views over Belfast if you go up Craigavon. But I mean, Spring Hill is about 1.5 miles from me, so. And I'll tell you the other thing, you have to catch it, because although it was perfect last night, there was drifting low cloud.
Yeah.
And I was dodging the cloud, it just appears, and all of a sudden it's there, so you have to seize your opportunity.
You do.
The best place is Giant's Ring. Yeah. I know people have reservations about going there for reasons we didn't go into, but if you're there in twilight, a perfect view to the southwest.
It's pretty good for me, Terry, but I think they closed the gate there I know there's a sign up there I saw recently, the gate's
closed. You get it even from the car park, but
you can't get to the car park.
Did they close the gate?
The road?
I didn't know that.
From the road.
At the bottom of Ballylesson Road?
There's a barrier down at the road.
I see, right. Okay.
So, yeah, I've thought about that myself, but you might have to do a bit of legwork.
Yeah, well, that'd be a long way to walk.
Park and hike up there.
Yeah.
Bolt cutters.
Hey guys, I'll show you mine from last night. This is from a car park in Ballinure, church car park in Ballinure, which that was that's my. It's off Facebook, but that's
very nice.
So
that's pretty good.
So that fits nicely now into a camera on the back of my 600mm f7.5 refractor. The whole thing.
That's pretty good.
41 arc minutes. I've got a similar one from the day before. That's 47 arc minutes. I haven't got one from tonight, funnily enough.
What exposure was that, Paul?
That is, well, it's actually that's a frame of video, and it's half a second at ISO 800 in that scope. Half a second is the longest video shot I can do.
Because as they get closer, you can use a higher magnification and reduce the background brightness, and that should bring out the fainter satellites. I see you've got Titan there. You should also be able to get Rhea.
Yeah. I've looked at every frame and I haven't got Rhea. I've got Titan there.
The forecast for tomorrow night is good. The forecast is good at the minute, so I mean it's worth having a try run.
Yeah. And on the 22nd, they'll also be pretty close, but they'll be that little bit lower down in the sky.
Yeah.
So good luck to everybody.
Indeed.
And you. What size did you say your scope was, Paul?
Well, it's an 80mm refractor, so of 600mm focal length, so it's 7.5. It's a standard Celeste 180 ED.
I was trying to visualize a 600mm diameter.
No. Oh, that would be good. Yes, I get not so much in, but I get lots of reflection, galaxies and everything there.
Yep. Best wishes to all for it.
Right. And if not, mark 2080 for your diary for the next really close one.
Yeah. It's no good because it's in the morning.
Paul, you're on morning shift. You might have got your golden handshake by then.
I hope I'll get it much sooner.
Okay, folks, I'm going to head off and get some dinner. So good luck to everybody, and we'll see you in January. And happy Christmas.
Thank you.
January it is. If you are going to, yes, if you are going to a site, let me know, because we'd like to see this as well. And I was thinking maybe up at on the the cafe place there up at the top of the hill, which is just around the corner from me. But I was actually thinking there's a nice southern, southwestern sort of view. I go out by Dundrod, and it's usually off the beaten track. It's very, very good skies, very, very good views there, and it's not that far away from where the cafe is. Do let us know, folks, because we'd like to see that. I really would like to be there and witness that. Indeed, I don't think it'd be around for the next one. So
I'll be down in Dublin, so where I go won't really be of any interest to anybody here. But do check out your place before before you're heading out. Check out a day or two beforehand. Right? Cheers, folks.
Excellent.
Bye.
All the best, Harry. Bye now.
Exactly?
Excellent talk indeed tonight as well. Very technical now, you said I found myself a bit out of my depth, but it was very good all the same. Very good indeed.
Was indeed. Jerry, you mentioned Dundrod. Whereabouts exactly?
Oh, it's let me see. I forget the name of the actual road now. Bally. Oh my goodness. If you go past the pits, just past the pits, and as soon as you are just past where the main pits is out of Dundrod, there's a small lane turns into the right. And if you follow that, there's a house on the right-hand side of that, or the left-hand side. If you follow that lane on round, and it takes you to, there are lanes that run parallel to the Dundrod Road, and a couple of laybys there, away from traffic, away from lights, very, very good view. I've got absolutely fantastic images. I could not believe the images of Mars and the planets. It got really, really clear, crystal clear. So if the weather's half decent and it's clear skies, it's an excellent spot, and it's away from, as I say, the light pollution, which is excellent, you know. So
if I'm checking out the Divas Cafe, I'll take a run up there as well. So thanks for that.
Well, let us know and we can maybe coordinate that. But I find it's a good site now. It's just like a lay-by of the road, of a lane. It's like a lane off a lane, but it's for dark skies and for clear skies as well. It's absolutely brilliant. Yeah, very, very little chance of light pollution, and I've, as I say, had some very, very good viewing there as well. Very, very good observing.
Could you send us a map reference or something, Jerry, for it?
I will actually, and I'll actually get the names of the. I should know them. We used to walk the dogs there for about 30 years, so I will give you some map just what it is. But I find it handy. I find it very, very good. And compared to sites, if you're away from Belfast, if you're too close to Lisburn or Belfast, the light pollution's terrible. It really just drowns out an awful lot of stars and nebula and things like that. So this is like in between. You can see the glow from Belfast, Lisburn, and Antrim, and sort of in between all those places. You know, it is a good dark spot. So it's not too bad.
It's okay for the southwestern sky, is it?
Yes, it is very good. You're right to the horizon. Actually, you're actually looking right across Loch Ness and towards the west and away towards. My goodness, Donegal in the west of Ireland. Basically, it's a near enough a clear view from there. So it would be an elevated site, and you're looking right down, right across. But it's, as I say, it's very dark skies indeed, and away from light pollution, which I found was one of the worst things for quality and for the actual image and things like that. If you're looking for stuff, you can't even find some of the stars if you're on the outskirts of Belfast, and the light pollution's atrocious. So it's not a bad spot. It's off the beaten track, and it's okay. So
right.
I'll let you know, and I'll get you. I'll actually I'll give you directions to that as well. I'll email those to you folks, and just to let you know where that is, where I would go.
That'd be good.
So it's
okay.
Yeah.
Good job.
But again, excellent talk, and nice to get talking to you, and hopefully just keep the fingers crossed that it's half decent. So excellent, folks. Thanks. I'm going to head on now myself. Good to get talking to you. Bye now.
Bye.
Okay, true. All right, talk to you next year.
Yeah, I have a couple of little vandals here. I have to go and sort out.
Right. Okay.
So.